Hello again, and today we're going to be going over a double integral over general regions. And so I did steal some of these from the notes. Thank you, Professor. And so by definition, a region R in the xy plane is a regular x region if there exist functions f of x and g of x and numbers a and b such that, and then here we have r equals the function g of x, and so this is like the y-axis. This is regarding y, so the bottom function and the top function, so you'd plug that into here, and then a and b, so this would be like across the x-axis. And then a region R in the xy plane is a regular y region if there exist functions hy and ky and numbers c and d such that R equals the left function is less than the right. You will see that. And then as c is less than or equal to y, as y is less than or equal to d. And so here again, double integration. Over a general x region, we typically see the functions behave like this, has more of a horizontal behavior. And then if it were over a general y region, they're more vertical like that. And so here, I did make a little note myself when splitting. When solving for the x region, you solve for the dx last. So, yeah. Yeah, sometimes questions will look like this. We'll ask you to identify what's what, f, x, y, all that good stuff. And yeah. And so here we see, here's a problem I have written down. So we have the double integration of x squared plus y squared dA. And so here we have, so these are our boundaries that we put on the integrals. And so in this case, it makes sense to solve it according to the x region, because for y here, we see that we have a 5x. And so we can't solve for this last, because if we solve for this last, then we're going to be left with an x when we need a real number as an answer. And so we're going to be solving for the x region, and as it was just mentioned right here, when we solve for the x region, we solve for dx last. And so we reserve x for the last part right here. And so this is how I set up my equation, because like I said, we're solving for y first and dx last. We're going to be solving for that y equals 5x, or y, as y goes to 0 and 5x, you have x squared plus y squared dy. And so we are now solving, and it is what I always like trip up on is to immediately cancel out x2 like a derivative, but because we're going backwards, essentially we are adding a y, because if it was x2y and we found the derivative of that, it'd be x squared. And so we add the y, and this turns into 1/3 y, or it could be y divided by 3 to the 3rd power, but yeah, just to keep it cleaner and more simplified, we'll keep it like that. And so now that we have the integral, or that we integrated our function now, we're going to plug in 5x and 0. Because 0 takes everything to 0, if we were to plug 0 in here, it'd take it to 0, and if we were to plug 0 here, it'd take it to 0. So we know that x2 times 5x plus 1/3, 5x to the 3rd, we're going to have 5x cubed, and that's because we have an x right here, and then 2x is here, so adds up to 3. And then this turns into plus 5. I'm going to take the x out. 3. Wait, actually, no, this is not one. Oh my god. So 5 cubed, if I'm correct, is 125. Let me double check that. $125 or 5 cubed. Yeah, 125 over 3. What is it? X, because the x is also to the third power. And so this is what we get after plugging in 5x. Yes, and we don't need to plug in 0 because we know it goes to 0. Okay, let's move to the bottom here now. We have, now we're solving for 5x3 plus 125. 3x to the third dx. So messed up. Okay, and I know that 5 can go into 125, obviously. So we'll pretend there's a 1 here. I'm going to multiply by 3. So we can combine like fractions and to make it easier on ourselves. So with that, we get 15 over 3 x to the third plus 125 to the third plus 3. We add that, we get 140 over 3 x to the third. So now we're solving for this integral. Boom, simplified it, and now we're just looking at one term. To make it even easier on ourselves, I'm going to keep that 140 over 3 outside of the integrand, just to make it easier on ourselves. I'm going to put 4 here. And I'm going to go ahead and solve for this. So I'm going to plug in, or this is equivalent to this as well right here. And we have 1 to the 4th. This is equal to 16 over 4 minus 1/4. We get 15 over 4. And so now we don't have any more x's. We can just multiply 140 over 3. There we go. We have 140. We have 140 times 15, which is 2,100 divided by 12. And that equals 175. So integrals are essentially like the area of, like, in between two fractions, or two functions. We're just looking for that space. I'm gonna highlight it. We're just looking for the space right here. And so in this case, these lines are not accurate, by the way. I'm just drawing willy-nilly. Like if this is what the two functions look like, and this would be 175 feet, etc. Yeah. And yeah, that's how you set up and solve for double integrals over a general region. This is definitely one of the materials I struggled with the most out of, I think, everything. It was between this and Lagrange multipliers, to be honest, but after putting a little bit more effort into that, I understood that. I think what also gets me is just ensuring that I remember the difference between the general y and x regions, and then also sometimes it's x regions, but it'll be like y will when we have certain points or something, we'll have like y equals x squared, and then we need to get the x instead. We need to get coordinates, so that y equals squared, we need to turn that into, let's say, like square root of that, so we have x equals the square root of y. And so just those little intricacies, but I think as I proceed to study the material, just understanding what this means and how to digest it and dissect it when I see it on the exam. And then also I do expect some similar problems to be shown on the exam, such as this, or maybe potentially a little bit harder with maybe like a square root up here or something along those lines.